Welcome to Tollefson Physics. So what we're going to look at today is a very special kind of motion called simple harmonic motion. And you've probably seen things that have simple harmonic motion. With me, I have a pendulum. And so this pendulum swings back and forth and keeps swinging back and forth, back and forth, back and forth. So it has a consistent motion. It keeps doing the same thing over and over again. Now, of course, in reality, that's going to have a little bit of dampening to it, which means that height is going to get less and less and less over time. If you see a really big pendulum at something like at a science museum, you'll notice that it actually can just keep going pretty much all day. They'll reset it each night, but it just keeps going and going and going. So we're going to be modeling the perfect case of simple harmonic motion, meaning that we're not going to lose any energy to its surroundings. And so what is simple harmonic motion? Well, simple harmonic motion is repetitive. It's periodic. It keeps repeating all the time. And so with the pendulum, keeps going back and forth, back and forth, back and forth. What else is important? Well, the net force is proportional to its distance. That is, the force as it gets higher is proportional to how high it is. And you can also think about that in the case of a spring. If you remember what Hooke's law was, is the force of a spring equals the spring constant times its displacement. So that is proportional as well. And then the last thing is the restoring force has to be in the opposite direction of its displacement. And so for example, with the pendulum, this is being displaced upward, but its force is pulling it downward. Same's true with the spring, and that's why there's a negative sign in Hooke's law. Is you stretch the spring one way, the force tries to pull it back to where it started in its equilibrium position. All right, so it's periodic. The net force is proportional to its distance from equilibrium, and its restoring force is in the opposite direction of displacement. All right, so here's a couple terms that we're going to need for simple harmonic motion. First one is period. How long does it take for it to go from its starting point all the way back to its starting point, going in the same direction? And so you can measure the period anywhere. There's certain spots where it might be easier to measure, but it's just that amount of time for one full cycle, and typically that's measured in seconds. Now the frequency. So frequency, you might say on a radio dial, it's measured in something called hertz. And what it is the number of cycles or oscillations per second. So it is the reciprocal of the period. And the units that are used is something called hertz. And hertz is just 1 divided by seconds. And so the equation is the frequency equals the reciprocal of the period. And then one other thing, it's a little more associated with circles, is something known as angular frequency, because you can model the oscillation as kind of a going around a circle one time. Now recall that the distance around one circle is 2 pi radians. So angular frequency is something in radians. It's radians per second. So we take the frequency from above and we apply it to a full circle, which means the angular frequency is 2 pi times the frequency, and that is measured in radians per second. So here's a quick example. Example being, let's pick a period of 4 seconds. It takes 4 seconds for the thing to vibrate back and forth once. So the frequency is the reciprocal of that. And so that's 1 divided by 4 seconds, which is the same as 1/4 of a hertz. Well, the angular frequency is now going to take that regular frequency, which is in hertz, and it's going to convert it to radians per second. And so you multiply that by 2 pi, and you end up getting 1.57 radians per second. So that's the number of radians it takes, or the number of radians it takes to travel, well, time for 1 second. Okay, so now, given the definitions that I had for simple harmonic motion, I want you to think about which of these exhibit simple harmonic motion. Hint, there's 3 of them. All right, so it turns out the pendulum is an example I showed you that is in simple harmonic motion. A mass that's vibrating on a vertical spring is actually simple harmonic motion. And believe it or not, a ball rolling back and forth, it starts up slow, goes fast, and then goes slow, goes fast, goes slow. So it's going back and forth in a bowl. That is also simple harmonic motion. What about a bouncing ball? Well, a bouncing ball abruptly turns direction, which doesn't happen in any of those other cases. So that's not actually considered simple harmonic motion. Or rolling a ball up the hill, it's going to turn around at the top and come back down, but there's nothing to cause it to go back up top. So that's not simple harmonic motion. All right. So I hope that this uh, gives you an idea of what simple harmonic motion is. And then what we're going to do is we're going to apply that to energy, forces, and even be able to calculate the period of different simple harmonic motion.